Hi everyone, welcome to the second lecture. In this lecture, we will cover the machine learning basics. But before that, let me clarify a few things. First, this is not a programming course. We do introduce Python to demonstrate how machine learning works, but we don't need to be adept at it. Second, this is not a machine learning course, but basic knowledge about what is machine learning and some basic ideas of machine learning algorithms will be briefly introduced. Okay, let's get started. The first thing I want to talk about today is the differences between statistical modeling and machine learning. Statistical modeling is the formalization of relationships between variables in the form of mathematical equations using traditional statistical tools such as significance, inference, and confidence. Machine learning algorithms learn patterns and trends directly from data without relying on any prior hypothesis. Here, I offer you a comparison table between statistics and machine learning. We will compare them from different aspects. First, in terms of predetermined hypothesis, statistical modeling must have hypotheses of the underlying relationship between variables. In contrast, machine learning doesn't need hypotheses determined by researchers. Because machine learning is a data-driven approach, the algorithms learn the data pattern directly from data and use the patterns to make predictions for the new data. Okay, let's move to the objectives. Statistical modeling aims to test your hypothesis about the relationships between variables using the data, while machine learning develops models that make the most accurate predictions. So machine learning focuses more on making predictions, and statistical modeling is more about explanation. Of course, statistical modeling is also able to make predictions because its performance is measured by how close the data points fit the prediction line. But the performance of machine learning is measured by how well it solves certain problems like predicting fraud. And actually, as long as the models make good predictions, machine learning doesn't care about the model's interpretability. Now, let's look at the directions of the timeline. The statistical modeling is rearward looking, while machine learning is forward looking. This distinction is actually determined by the focus of the two. Machine learning focuses on making predictions. We train models using the past data, and we make predictions for current and future data. In contrast, we train statistical models to quantify the relationship between the variables, and that relations only exists in the past data. Of course, we want that relationship to hold in the future, but statistical modeling is often more about describing data in the stage of data collection. In contrast, machine learning is more about projecting the data into the future. As for the data size, machine learning models need more data to perform well than statistical modeling. In general, the most powerful machine learning models, such as random forest and neural network, are trained using thousands or millions of data points. In contrast, statistical models often use only dozens or hundreds of data. And the next one is the number of variables. Machine learning outperforms traditional statistical modeling when there are many variables. And in extreme case, when the number of variables is greater than the number of observations, the statistical modeling totally fails, but machine learning models can still proceed. In terms of the data structure, machine learning works well with unstructured data, but statistical modeling can only work with the structured data. As we learned last week, Machine learning models such as neural networks can directly handle the unstructured data like videos, audios, and images. For the number of assumptions, statistical modeling requires many assumptions, while machine learning requires only very few assumptions. To take the linear regression as an example, the linear regression assumes linear relationship between independent and dependent variables, and also it assumes the error should be IID and so on. But machine learning algorithms has much fewer assumptions, although it does assume a few things. But in general, they don't have to follow most of the assumptions. For example, naive Bayes is one kind of machine learning algorithm, and it performs quite well in real life, even when it breaks its assumptions. So the biggest advantage of machine learning is that we don't have to specify the distribution of independent or dependent variables. And machine learning has stronger prediction power because it uses more data while it needs fewer assumptions. And finally, for the evaluation of the models, machine learning requires to use the testing set to evaluate the models. But statistical modeling doesn't have the concept of testing set. Okay, so we have distinguished the statistical models and the machine learning. Then we are able to cover some basic concepts in machine learning. As we said before, machine learning is a computational method that learns patterns in large dataset and then make predictions. It traditionally consists of two major tasks, the supervised learning and unsupervised learning. In supervised learning, one is presented with a set of data consisting of input X and a corresponding output Y to construct a classifier or regressor that can estimate the output value for previously unseen inputs. When the Y are qualitative, it is classification problem, and we draw a line to separate the two classes, or draw lines to separate multi-classes. When the Y are numeric, it is regression problem. We draw a line to fit the data points. In unsupervised learning, one tries to infer some underlying structure from the inputs, given no output labels, or values, given no output values. Actually, there are two more advanced machine learning types. The semi-supervised learning, where part of the Ys are known, and the reinforcement learning, which instead of getting examples, the algorithm gets reward for doing good things and gets punishment for doing the wrong things. One example of reinforcement learning is AlphaGo. The software uses the reinforcement learning to learn which strategies are good based on whether it win or lost the games. Okay, now let's see the two basic problems in the supervised learning. The classification problems and the regression problems. The classification problems dependent variables are often called labels or categories. The regression problems output are continuous variables. And for classification problems, it aims to predict the class or category for a given observation. And when the problem has two classes, it's called a binary classification problem. And when the problem has more than two classes, it's called a multi-class classification problem. In contrast, regression problems aims to predict the quantities for a given observation, such as the amounts and sizes. Finally, a predictive model established to solve a classification problem is called a classification model. A predictive model established to solve a regression problem is called a regression model. Okay, now I'll give you an example of supervised learning. Classification is the most common type of supervised learning or machine learning. It takes an input, like a picture of cat, and a class label, like the word cat, to train the model. So the model actually, the algorithm takes the inputs and the outputs to learn the data patterns and get the model. Then, once the model has been trained, you can give it a new input, such as a cat picture, and then the model will generate the class labels for the instance. Whenever we train a model on examples of input and output, we call it supervised learning. But sometimes we don't have the labels, we only have the X. Then we use the machine learning algorithms to learn the data patterns and get it to figure out the categories. And this is called unsupervised learning. Okay, so in summary, machine learning uses a variety of algorithms to turn a dataset into a model. They are engines of machine learning. They can tell the machine how to retrieve, receive, and analyze input data to predict output values within an acceptable range. The learning tasks may include learning the function that maps the input to the output and learning the hidden structure in unlabeled data. And you may ask what kind of algorithm works the best. Actually, it depends on a few things, like the kind of problem you are solving, the computing resources available, and the nature of the data. But nobody can tell you before making the experiments which kind of algorithms work the best. And that's why you often see in a research, the researchers often try a few algorithms and compare their performance using different metrics, then to decide which one performs the best in this setting. Okay, in this slide, I give you some examples of regression algorithms and classification algorithms. You may notice that for several of them, they appear in both categories, like the artificial neural networks, decision trees, random forests. They are both regression algorithms and classification algorithms. The artificial neural networks, actually, we mentioned this last week. It comprises units or neurons arranged in a series of layers, and each of them connects to layers on either side. And actually, these neural networks are inspired by biological systems, such as human brains, and how they process information. Decision tree is a flowchart-like tree structure that uses a branching method to illustrate every possible outcome of a decision. Each node within the tree represents a test on a specific variable, and each branch is the outcome of that test. Actually, decision tree is the most popular machine learning algorithm used in today's business, since it is of high interpretability. Okay, the next one is the random forest, which is an ensemble learning method. Ensemble means it's a combination of different models. The predictions could be generated either by majority voting or by taking the advantage of individual models. An ensemble learning method combines multiple algorithms to generate better results for classification, regression, and other tasks. For the random forests, It is an ensemble learning method based on decision trees. So it first generates a forest of decision trees. Then each decision tree uses a subset of randomly selected attributes or variables, and then it aggregates the decision trees to yield the most efficient predictor. That is why random forests often outperform the decision tree. For the classification algorithms, the logistic regression is another technique borrowed from machine learning, borrowed by machine learning from statistical modeling. And this is used to solve binary classification problems. Naive Bayes. Naive Bayes is based on Bayes' theorem and classifies every value as independent of any other value. Support vector machine. This is a very complex algorithm, and we will discuss in the future, but the main idea is that it filters data into categories by providing a set of training examples, and each set marked as belonging to one class. The algorithm then builds a model that assigns each value to one category. Okay. In this slide, I offer you an algorithm mind map. So you can see there are many different algorithms, but actually in real life, we have much more algorithms than we see now in this map. But what I want to say is that you don't need to worry about this because it's unnecessary for us to understand every algorithm in machine learning domain. We only need to know the most popular one and how to apply them in our work and life. Because the objective of this course is to understand how to apply the AI or machine learning in our life and work. So in this course, we will cover the most popular, most important ones. So don't worry about the others. So how to evaluate the models? How to tell if the model is good or not? Here, we need to introduce the concept of metrics. The evaluation metrics are used to evaluate the predictive performance of the established model. There are two categories of the metrics: the metrics for regression models and metrics for classification models. First, let's look at the metrics for classification models. Here, I offer you only 9 metrics for classification models. There are many more, but these are most commonly used ones. First, the true positives. True positives are the cases when the actual class of data points was 1 or true, and the predicted is also 1 or true. Here, I want to explain 1 and 0 are often used as the labels for binary classification problems. And we also often label the class of our interest as 1 and label the class which we are not interested in as 0. The true negatives means the cases when the actual class of data points was 0 and the predicted is also 0. False positive refers to the cases when the actual class of data points was 0 and the predicted is 1. False negative means the cases when actual class is 1 but the predicted is 0. Here in this slide, the recall, precision, and accuracy are highly related concepts based on the true positive, true negative, false positive, false negative. First, the recall, aka sensitivity, is the fraction of relevant instances among the retrieved instances. You may find this is difficult to understand, right? So the first approach to understand this concept is by looking at this picture. So the recall is this true positives, this area divided by this area, the relevant elements. Or you can remember this by using this equation. Recall equals the number of true positives divided by true positives added by false negative. Second, the precision, which is also called positive predictive value, is the fraction of relevant instances that were retrieved. So in this graph, it is this area divided by this area. Or you can get the precision score using this equation, the true positive divided by true positive and the false positive. The accuracy is the proportion of correct predictions, including both the true positives and true negatives among the total number of cases examined. So in equation, it equals the true positive and true negative divided by all the cases. The next metric is the ROC-EUC. What is ROC? It is a curve named Receiver Operating Characteristic Curve. So as you can see in this graph, it is this red line. The x-axis is a false positive rate, and the y-axis is a true positive rate. The curve is generated actually by changing the threshold. So we can link different points indicating different threshold at different threshold to get this line. And the AUC is exactly the area under the ROC curve and above the x-axis, which is the yellow area in this picture. Finally, F-score. F-score is a harmonic mean of precision and recall. So this is actually a very good score, very good metric, because it takes consideration both the precision and recall. So that's all about the classification models metrics. Then for regression models, we have two important metrics, the mean absolute error and the RMSE. The error here refers to the residuals, which is the difference between the actual value and the model's estimate. But to evaluate the model's performance, before using the metrics, there is another important thing to do. We need to make sure we evaluate the performance of models using new data rather than the data we used for training. This is because if we use the same data to test as we train the model will remember all the instances when in the training stage, and thus its performance will be inflated. It's the same as letting students take two quizzes with the same questions, and you will find the students do very good in the second quiz, right? So when we are building a predictive model, we need to evaluate the capacity of the model on unseen data. This is typically done by estimating the accuracy using data not used to train the model. So for data splitting, we partition the data into a training data set used to prepare the model and a test set to evaluate the model's performance. Here, for the training and testing, we need to understand what is training and what is testing. Train means the algorithm learns from the data to develop the model. And the test means we use the developed model to predict the variable on the test dataset. Then evaluate the model's performance by comparing the predicted value with the actual value. So here are two kinds of data splitting techniques. One is directly partition the data into training set and testing set by different percentage. Usually when we use 80% as training set and 20% as testing set. The second technique is called k-fold cross-validation. Cross-validation is a resampling procedure used to evaluate machine learning models on a limited data sample. The procedure has a single parameter called k that refers to the number of subsets that a given data sample is to be split into. So we call it k-fold cross-validation. Often we use 5-fold or 10-fold cross-validation, where 10-fold cross-validation have 10 iterations. And for each iteration, we use a different test fold. We use a different fold as the test fold and the remaining folds as training folds. And for each iteration, we get the performance metrics. And after 10 iterations, they average their metrics to get the cross-validation performance metric. So cross-validation is primarily used in applied machine learning to estimate the skill or performance of a machine learning model on unseen data. And we can use a limited sample to estimate how the model is expected to perform in general when used to make predictions on data. And this is a very popular method because it's very simple to understand, and it generally results in a less biased and less optimistic estimate of the performance of the models. And importantly, each observation in the data sample is assigned to an individual group and stays in that group for the duration of the procedure. And this means that each sample is given the opportunity to be used in the holdout set one time and used it to train the model for k-1 times. Here I give you a link of example of machine learning experiment. And the Kaggle website is actually a very interesting and useful website for machine learning researchers and students, where they have they offer us many public data sets and some competitions. Okay, let me show you this website. So if you go to the Kaggle website and go to the competition section, you will find there are many competitions. For example, for starters, they have Titanic machine learning from disaster, where they use the customer's information to predict the survival. And also they have house price prediction and many interesting competitions. And if you click dataset, you can find there are many trending datasets, like also have Omicron daily cases by country. And you can use this to train your models and make predictions. Here as an example, if we see this Titanic classification competition, you can go to the code to see others' work. Okay, so maybe, yeah, so like for this notebook, it used the Python 3 as a coding environment. So first, it imports some Python packages. Define its problem, load the data, analyze the data, clean the data, select features, choose models, and visualize and discuss the results. So yeah, so they will introduce their workflow, and you can see how others deal with the data. So here, they load the training dataset and testing dataset. So they have already partitioned the dataset in this competition. And often the cases, we start by analyzing the data, the training data, or do some exploratory data analysis. So here it shows a data frame. You can see the records. You can see the variables, including the name of the passenger, the sex, the age, and so on. So these are variables that we can use to make the classification. And also you can see the number of records is over 800, and the predictors, the attributes or the variables number is 12. We can also describe the data set, see the information of the data set. And then we can conduct some pre-processing, like dealing with the missing values, looking at the numerical features and the category features. For category features, we usually need to do additional pre-process. So like vectorize these categorical values. And here you can see some exploratory data analysis, EDA. This is to get a better understanding of our data set. Yeah, and here we can get dummies. Use this function to pre-process the categorical values. And here in this step, we define the models. Like here, we use the random forest as the classification algorithm, and we choose certain parameters for this model. After that, we fit the model or train the model using the training dataset. And with this trained model, we predict the classes on the test dataset. And we can output the results to a CSV. So that is a very simple example of machine learning experiment. And you can also go to their website to find the computations and datasets and try yourself or look at what others are doing. Okay. So to conclude, in this course, we talked about the differences between statistics and machine learning. We covered the basics of machine learning, including the classification, regression problem, machine learning algorithms, evaluation metrics, and data splitting.